Okay, welcome. It's time to get started. Tonight, we are starting the last topic in the course, which is solving ordinary differential equations by Laplace transforms. Tonight is going to be packed with a lot of calculations, a lot of formulas. We need them to get started with this subject, and hopefully we'll be at the point by the end where we can solve at least some simple differential equations by Laplace transforms. That tends to leave an impression which is not accurate and not helpful, which is number one, Laplace transforms are tremendously inconvenient, and number two, that it is just so much easier to do it some other way. Well, that's true. If you solve the kind of equations we already know how to solve by Laplace transforms, you'll probably quickly decide you'd rather do it the other way. But Laplace transforms allow us to deal with some kinds of functions that we can't deal with up till now. As a matter of fact, functions that just don't fit into the calculus of elementary functions. By elementary functions, we mean all the algebraic stuff, polynomials, powers, roots, sums, differences, quotients, and then you throw in the rest of the elementary functions, trig functions, exponential, logarithmic, and that's all that comes to mind right now. So you think, well, gosh, that's everything, right? Well, no. If you think about, say, we have a circuit that powers the lights in our ceiling. Now, when I come in here and open the door, it's dark, so I switch on the light. Now, what that means is we go from having absolutely zero input into that circuit to, mathematically, we would say 0 time. Of course, something's happening there under the hood, but a good model is to say you go from having 0 voltage input to having a sinusoidal input that just turns on in a moment. So we would like to be able to model those kind of functions. They're just 0 for a while, and then they turn into a sine function or exponential, or they go to a spike and then they turn into a decaying exponential or something like that. So there's all these kinds of functions that would be natural in especially electronics, that first comes to mind, but in physical systems as well. If we think about the mass spring system, how would we model that if we had it in static equilibrium? So we have our weight just hanging and it's stretching the spring a little bit, but not past its normal capacity, and you walk up to it and you very accurately give it a rap with a hammer on the bottom that drives the weight up suddenly. Well, what you've done is the same situation. The input on that system was 0 until, in a moment of time, you imparted energy which accelerated it almost instantaneously. So you have a 0 input, and then suddenly it has a velocity and it has a position, and now it's going to do whatever it's going to do. And of course, in vibrations, you kind of have that situation over and over again. You could have a weight suspended by a spring, and then if it's against a surface that's vibrating, it's going to keep hitting it over and over again and putting these kind of impulses into the system. Well, we don't have any way to model a function that would impart a finite amount of energy to a system in essentially 0 time. How do you do that? It's some kind of discontinuous function, and is really discontinuous. So we are going to learn how to handle those kind of functions with Laplace transforms. And that's really the motivation for working with them. So with that, we are ready to begin the discussion of Laplace transforms. Let me just make a couple announcements, though, before I jump into that part of the lecture. Number one, I have graded everything. As far as I know, I've graded every paper that's been submitted to me, and they've all been returned now, either by email or in person. So if there's something you haven't gotten back, you should let me know, because I don't know about it. Okay. Secondly, we are nearing the end of the course, right? I think it's this week and next for lessons, and then just the final exam. So I'm going to try to move through this material on Laplace transforms as efficiently as I can, so that we have at least a little bit of time to talk about how to prepare for the final. Not a week from today, but 2 weeks from today is the final exam. That was originally announced as Thursday in the syllabus, but then I found out that I'm not allowed to do that. I'm supposed to have the course grades in sooner than that. So I can't wait till Thursday to do it. I thought it would be very nice to have a full 2-hour period to review, and you'd have the weekend prepared. Well, it would have been nice, yes, but it's not going to play out that way. So with that, we're ready for Laplace transforms. Okay, I am going to start with this little diagram I drew here. And there is something like this in the printed notes, which I will post after class. And you'll see something like it if you have a copy of Craig's book, and I'm sure you can find it in a million other places either. Also, this is by no means original on my part. Laplace transforms, the big picture is this. We have an ordinary differential equation. We have a problem that we want to solve. Now, what we've been doing up till now is using techniques from calculus to go from the problem direct to a solution. With Laplace transforms, it's a totally different approach. What we have is, you could sort of think of this up here as T space. In other words, functions who have that are functions of the variable T, and we're just working with those functions directly to get over here up till now in the course. There's another strategy you can use, and that is to use what's known as the Laplace transform. You can transform this problem in ordinary differential equations to a problem in algebra. And as long as your ODE is not above second order, then at least any polynomials you have to work with will not be above second order here. And that's good. We know how to factor, and we know how to find roots even in cases where they're complex, if you set a polynomial equal to 0. So we're going to transform that to an algebraic problem, use techniques of algebra to get the solution, and then transform back to get the solution of the ODE. This does tend to be kind of a circuitous route. There's multiple steps. You gotta start with your problem in T space. You turn it into and it's a calculus type problem in T space. You turn it into an algebraic problem in S space, solve the algebraic, and then you have to move back. So there's a lot of work here, and the algebra and the arithmetic can get really intense. As a matter of fact, if you're working on practical problems, you might very well find yourself frequently making use of a computer algebra system, just because there's so many pieces to keep up with. There are essentially 3 prerequisites we need to get through, and we're going to try to get through them at least at some level tonight. in order to start solving ODEs. And that is, first of all, you got to know how to transform the common functions of science and engineering. And we have some notation for that. You use kind of a script L. And traditionally, when people write by hand, they use curly brackets here. And so this f of t is a function that's involved in the ODE. And the standard notation is this: you use lowercase for functions of t and uppercase names for functions of s. And we do traditionally use t for the variable in the ODE, and then s for the variable in after you've transformed it with the Laplace transform. Now, of course, there's no reason you have to do it that way. You could use x here, and I don't know, a w here or something. It would be fine. It's just that if we have some system, then you start getting more signals when when you're looking at a function of s, you know where you're at in the problem. You've already made this jump from the t space to the s space, so you're working on the algebra problem. So it's, especially when you're starting, it's really helpful to stick with the standards, and then later, if you want to mix them up, that's fine. People do it all the time. The next thing we need to know is how to transform derivatives. If you think about it, an ODE is going to be involving some unknown function. Typically, we write it as y of t. Well, just because we know how to transform things like e to the t and cosine of t and stuff like that, it doesn't mean that we know how to represent their derivatives. So at least for tonight, we need to know how to take the transform of the first and second derivative of a function. And then if you think about it in the picture here, you do the transformation from t to s space, you do some algebra, and it tends to be a lot of algebra. And then once you got your algebra done, you want to push back to the t. So now you need to be able to compute an inverse transform, which means you got to be able to, given that function in its transform state, you need to know how to get back to f at t. So those are the big three things that we're going to be doing here tonight. And if you're a big picture person, I hope that will help you with the outline of what's going on. And in fact, that's essentially how I'm going to give the lesson. And then at the end, we'll solve a few simple differential equations. I tried to come up with a moderately complex one that wasn't horrid to do, and I didn't succeed. I can get a moderately complex one that is horrid to do, but or a horrible one that's extraordinarily difficult to do, but one that's got a little bit of complexity, but not too much. Well, I didn't get there. Okay, so we are going to start out by talking about the gamma function. Gamma function of traditionally people define this with the Greek letter nu, because it kind of goes with an n in English. So gamma of nu is defined as the integral from 0 to infinity of e to the minus t to the nu minus 1 dt. And I think the first time I saw this, I thought, what? Why would anybody in their right mind care about such a thing? This is an improper integral, first of all. And then, you got powers of t times exponentials. Well, I remember those from calculus. It's integration by parts, maybe 4 times in a row. And, do the problem 3 times because you hope you get the same answer twice. And well, it turns out that this thing is actually tabled, and there are calculator routines online that will allow you to evaluate this. But it's very useful theoretically. As a matter of fact, it's going to pop up in some of our calculations tonight. And it was in the homework problem where I gave you a series representation for a Bessel function of the first kind. And it was buried in there. You didn't see this symbol, I don't think, but at least that I gave. Some people looked it up and had it in there, which is fine. What we're going to find out in just a moment is this: that gamma of nu plus 1 turns out to be nu times gamma of nu. We are also going to find out, and I'm actually going to do it here in a minute, but I'm just announcing ahead of time so you don't get lost in the detail. This nu, it does need to be at least 1. If it weren't, then you'd have a negative power on t here, and this function would blow up at 0. So nu needs to be greater than or equal to 1. Or sometimes you'll see this formula written as gamma of nu plus 1. And, it doesn't matter. It's just that this number here, you get this exponent here by taking that number and subtracting 1. So if you have nu plus 1 here, then you'd have t to the nu here. And you'll actually see it both ways. They're equivalent, but just be aware. And if in this form, then nu has to be at least 0. So the point is that inside the integral here, this t to some power, that power needs to be positive or 0. 0 would be fine, but not negative. So in this one. Okay, so let's compute some values of gamma. And now if we look at, let's take gamma of 1. Then if I look at my formula here, gamma of nu is integral from 0 to infinity, e to the minus t, t to the nu minus 1. So that'll be t, in this case, to the 1 minus 1 power. And this just turns into the integral of e to the minus t from 0 to infinity. Now, I want to review exactly that this has a meaning. It means this. It's the limit as, let's say, m, cap m tends to infinity of the integral from 0 to m e to the minus t dt. And I want to do this a little bit carefully once. We're going to be doing a lot of this tonight. So after this one, I won't slow down so much, but I want to just remind you of what the symbols mean that we end up writing more in a hurry. Okay, now the antiderivative of e to the minus t is minus e to the minus t. Whoops, I need to limit. So let me just come down to the next line here. So the antiderivative is e minus e to the minus t. And I'm evaluating this on the interval from 0 to capital M. And then I'm taking the limit as m tends to infinity. And when we do that, what will happen? Well, when you plug in m, you're going to get minus e to the minus m. And I forgot to write my limit again. So I will interrupt myself there and get it in. Okay, so I want minus e to the minus m. And then when you plug in the 0, you get minus that minus there. So plus e to the 0, which is 1. And then this is, and forgive me if you've seen the answer already. I just want to make sure that everybody's keeping up. Okay, so now what happens as m goes to infinity? Well, e to the m grows very, very rapidly. So you have -1 divided by a huge number. That is essentially 0 plus 1, and we get 1. So we've just gotten this much. Gamma of 1 is 1. So we've actually computed this function for one value. Now, I'm going to do one more just so that you can see in a concrete setting how this is going to work when we do a little bit more abstract. But then I'm going to get this recurrence relation right here. This gamma nu plus 1 is nu gamma nu. We're going to prove that, and it's actually quite easy once you catch on to how this works. So now we've got t to the 2 minus 1 dt. So it's just t e to the minus t. So this is a classic integration by parts problem from calculus, right? So probably you'd call this part u, t to the 1, and this part e to the minus t times dt. That's what we would call dv in calculus. So the antiderivative is uv, so that's t from this, v, antiderivative here, minus e to the minus t, subtract the integral, and now we need to evaluate that between 0 and infinity. And we're integrating from 0 to infinity, minus v, well, that's minus e to the minus t, so that gets switched to a plus. So we add that integral. Du, well, the derivative of t is just dt, and this no longer has that that power of t multiplying the exponential. So now we can go direct to the antiderivative there, and this we might as well evaluate. If t tends to infinity, you've got e to a very, very negative number. Well, that collapses towards 0, and that goes towards 0 exponentially. This, of course, goes towards infinity, but the t grows as a straight line, and the e shrinks as an exponential. So that exponential wins. It's much, much faster to converge towards its limit, which is 0, than the t is to converge towards its limit, which is infinity. Now you could prove that with L'Hopital's rule or something, but you could also just believe me. When you plug in infinity, you're going to get 0 there. Now, of course, it's not plugging in infinity. What it is this business taking the limit, but we think of it as plugging in infinity. Okay, now I'm going to subtract what happens when I plug in 0. Well, when I plug in 0, I'm going to get a 0 there times 1. So it's just 0 minus 0. This part right here contributes absolutely nothing to the integral. And this part, well, e to the minus t is the antiderivative. And once again, on the interval from 0 to infinity, and we do this kind of argument one more time. As t goes to infinity, we have 1 over e to a very large number. That goes to 0. And then it's minus a minus, so plus. When you plug in the 0, e to the 0 is 1. And we got 1 again. So this is what we got so far. Gamma at 1 equals 1. Gamma at 2 equals also 1. And now I'm going to go for this recurrence relation, which was way back here. Gamma nu plus 1 is nu gamma. And some people will probably be more comfortable if I change the letters, so I will in this case. Gamma n plus 1. But when I'm writing n here, I don't mean to imply that this has to be an integer. It doesn't. It could be like 3.7 or square root of 2 or pi, some such thing. Okay, well, its definition is integrate from 0 to infinity, e to the minus t, t to the n plus 1 minus 1, so that'll be n. And then, were we in calculus, we would say, hey, that looks like integration by parts. That's the u part, that's the dv part. So you want a uv, so minus e to the minus t. U is t to the n. Evaluate between 0 and infinity, minus the definite integral from 0 to infinity. V, well, that's another minus e to the minus t. And then du is n times t to the n minus 1 dt. Now, you could keep going on this, but that has meaning all by itself. So on that last integral, let me handle this part here. After you've done this a few times, you sort of expect the pattern, but we did it once and we just got zeros, right? And similarly up here, you just got a 0. So we kind of expect that to contribute nothing, but let's check. As t goes to infinity, you get an exponential. It's really 1 over e to the t. So that goes at an exponential rate to 0. So that one doesn't matter, it's polynomial. So you get a 0, minus 0 if you want. And then minus what you get when you plug in 0. Well, you plug in 0, this is a 1, but that's a 0. So once again, no contribution from the uv part of the parts formula. And then I've got n times this integral. But this integral happens to be exactly the definition of gamma of n. So here we have it. Gamma n plus 1 equals n gamma n. And that is enough for us to get all of the gamma function for all of the positive integers. You do it by, officially it's by induction. But our formula says this. Gamma n plus 1 equals n gamma of n. And this works for n greater than or equal to 1, I guess. Because I've got a gamma n here. Okay, well, I know, because I already calculated it, gamma of 0, not 0, 1. Gamma of 1, we computed that way back here. Gamma 1, and down at the end of the calculation, we got 1. And we also did this one. Gamma of 2, we computed that one. That's up here, and we turned out we got 1 for that. Now, what if we want gamma of 3? Well, the answer is it's going to be 2 times gamma of 2 by this formula right here. So set n to be 2. Gamma of 3 equals 2 gamma 2. But gamma of 2 is 1. So that's 2 times 1, which we recognize, of course, is 2 factorial. Gamma of 4, well, by the formula, you knock this down by 1, so it'll be 3 gamma of 3. So it's 3 times gamma of 3. Gamma of 3 we already computed. That's 2 factorial. 3 factorial. And at this point, you can probably see the pattern. Gamma of 1 is 0 factorial. Gamma of 2 is 1 factorial. Gamma of 3 is 2 factorial. Gamma of 4 is 3 factorial. In general, gamma of n, and now n does have to be an integer, a non-negative integer. Gamma of n plus 1 is n factorial. And the really nice thing is we now have a generalization of the factorial function. So you could effectively compute something like 3.5 factorial. Of course, that would be gamma of 4.5. But what is that? It's the integral from 0 to infinity, e to the minus t, t to the, now you knock that down by 1, 3.5 dt. And how would you do that? Well, I'll tell you how I would do it. I would either do it numerically or I would use some computer algebra system like, you know, Wolfram Alpha, for instance. I could go to that website and it will compute it for me. And for that matter, the gamma function is tabulated. And it has been for a long time. Before there was handy calculators, there were tables of this function. So, and by the way, you don't have to have a table that just runs forever. You know, that starts at 1 and goes on to thousands and thousands, because you can keep knocking this down. This gamma 4.5, well, you could use this rule. This rule right here, gamma n plus 1. So it's 3.5 plus 1. It's 4.5 times gamma of 3.5. And then you can knock it down again. It's 4.5 times 3.5 times gamma of 2.5. And you can knock it down one more time so that you get it on the interval from 1 to 2. So if you have this tabulated on the interval from 1 to 2, you can always compute the value. You just keep knocking these numbers down until you land in that range from between 1 and 2. And then you look it up on your, in the old days, you look it up on your paper table. That's what you did. And this function comes up enough in science and engineering that you really should have some knowledge of it. Now, should you memorize values? No. You'll just compute them in the way you do a sine or a cosine. You know? Use a machine for it. But you should at least be aware of some of the properties and that it is a generalization of factorial. Okay, so that's the gamma function. And it turns out that the reason I went over this was, well, multiple reasons. Number one, you should know about the gamma function. It's pretty useful. Number two, you really should know this recursion relation right here. Number three, it's the calculations that we're doing here are very much like you do when you compute Laplace transforms from the definition. Fortunately, we don't often have to compute them from the definition, but to get started, we do. Oh, and something, I just noticed something that I've been wanting to mention all course long, and I thought I never remember until afterwards. For those of you only attending online, I think if you look at my hand, you could say probably two things. First of all, the guy is apparently related to apes. And number two, he has a horrible case of skin cancer. None of those are true. It's the way this crazy camera works. If you saw me in person, you would see I'm sort of like your standard semi-old guy. And I am neither ape-like nor do I have skin cancer. At least if I don't have skin cancer, I don't. So, and that's my comic relief after the first intense round of calculation. Okay, so there is the gamma function. Now, Laplace transform. The definition of Laplace transform is as follows. Oh, and I should mention, if your native language is English, it would be very natural to pronounce this as Laplace, but this is, I think it was a French name. So it's, you know, like half the stuff in English, it came from some other language. So it doesn't follow English rules of spelling. So Laplace is as far as I know, how it's supposed to be pronounced. Okay, what is the Laplace transform? The Laplace transform of the function f at t is defined as the integral from 0 to infinity e to the minus st f at t dt. Now, a couple things to notice about that. Number one, it is kind of like what we were doing with the gamma function, right? In that case, we always had t to some power here for f at t. And secondly, we didn't have the s. But if you think about it, if you fix the s to be 1, then we would have been doing exactly the calculations involved in computing a Laplace transform. The notation, standard notation is this, f at s. And that's another thing to notice. This, this t, well, it's here and here and here. And when it appears there, it means the t gets used up when you do the integration, right? So you'll get different values of that integral depending on what s you choose. And that makes this a function of s. Whereas this one, inside, this started out as a function of t. So, okay. Well, that's the beast we're going to be working on. So why don't we just compute a Laplace transform, and I'll try to convince you that they're not all horribly difficult. So how about the function that's always equal to 1? And you can think of this as the first step in being able to take transforms of polynomials. If I can take a transform of 1 and t squared and t cubed, et cetera, then I can go a little piece at a time, and I can a term at a time, and I can get the transform of polynomial. So by definition, it's the integral from 0 to infinity e to the minus f st times 1, which of course you don't really have to write, dt. And well, that looks pretty familiar. The antiderivative is 1 over s, but it's negative, right? Minus 1 over s, e to the minus st on the interval from 0 to infinity. All right, so, and it's the t that's varying. So it wouldn't really hurt to label those values. T goes from 0 to t goes to infinity. All right, well, let's think about what happens when t goes off to infinity. Now, I need to make some assumptions here about the value of s. And that is, if there is nothing else going on in the problem, we always have this one. S is positive. If it were not, if s were negative, then this would be for positive t's anyway. And these, and by the way, you're integrating from 0 to infinity, so you are thinking about positive t's. If that s were negative, this function would grow rather than shrink as t goes off to infinity, which means this integral would blow up. So this thing is just not defined unless s is positive, or perhaps in some cases it might work when s is 0, as long as this function shrinks on its own sufficiently quickly. So here we're thinking of s as being a positive number. So this is definitely negative out here, this coefficient. And we want to plug in, take a limit as t goes to infinity and plug in 0 and get that difference. So we have minus 1 over s, might as well just put that by itself. And then let's work on the exponential. When t goes off to infinity, this thing goes to 0. When t is 0, you get e to the 0, which is 1. So I've got minus 1 times minus 1 over s. So that's 1 over s. And we have computed our first Laplace transform. The transform of 1 is 1 over s. And I think I'm going to start a table here. How about this? F at t cap f at s. And if the function is just the constant 1, then the transform is 1 over s. And we will come back to that and start filling it out and get a number of functions tonight. Okay, so we transform 1. Let's take the next step then. If we want to know how to transform polynomials, then we need to know how to take a variable to the 1 power. Well, that's the integral from 0 to infinity, e to the minus st, t to the 1 dt. Quite similar to some stuff we were doing with gamma function, but not quite, because you got an extra variable in here. Okay, same deal. We'll let that be u. Let this one with the dt be dv. So using the parse formula, uv, I need the antiderivative here, minus e to the minus st over s. You got a chain rule factor now. The u is a t minus antiderivative or integral from 0 to infinity, e to the minus st. Well, let's see, I should say what I'm doing. This is uv minus the integral of v. So antiderivative here, s in the denominator, and a minus, so that turns that into a plus, v du, which is just dt, and e to the minus st here, and this is a 1. And I need to integrate, t goes from 0 to t goes to infinity. Okay, well, now we've seen this so many times, we're kind of expecting this whole thing to drop into 0, but let's double check. When you use infinity on the e part, you're going to have e to a minus some constant times a very, very large number. So that goes to 0 for sure. If you want to keep track of that minus sign there, you can say minus 0. Then minus the result at 0. So we're subtracting a negative, we'll get a plus. And in that case, when you put 0 for t, the exponential becomes 1, but the t turns into a 0. So sure enough, once again, nothing from the uv part, everything from this integral. And this integral, well, I guess there's a couple of ways of looking at this. On the one hand, we could simply do the integral, right? So the antiderivative e to the minus st with respect to t is e to the minus st over s, but it's negative because you got a negative from the chain rule factor. So I need a minus there, and I'll put parentheses around here because I'm not subtracting those, I'm multiplying on the interval from 0 to infinity. And let's see, I've got 1 over s times. Now, actually, how about 1 over s squared? I'll put that s over with that one. And then at infinity, e, as t goes to infinity, e to the minus st goes to 0. And at 0, well, there's no t in here now, so that one does not drop out. And so this turns into a 1 on the top, but it's minus a minus 1, so plus 1, just plus 1. I already took the s out. So 1 over s squared, and we have our second transform. So t has transformed 1 over s squared. And if all you have to work with is this table, then there's an obvious guess for t squared. It looks like it'd be 1 over s cubed. It's not. However, it is related to it. So it isn't an entirely bad guess. So just keep that in mind. We're kind of expecting s cubed in the denominator, but you get something else in the numerator, and we'll find out why in just a minute. Okay, now we could go on for forever. You get the transform of 1, then t squared, then t cubed, then t to the 4th, and eventually 8 o'clock comes and we have to quit, but we're still not done. So so next class meeting we keep going. Well, you never get everything you need, right? So we're going to try to think of a more clever way. And why don't we do this the way we worked with the gamma function? What's the Laplace transform of t to the n plus 1? Let's work on that. and see if we can get a recurrence formula. Well, that will be the integral from 0 to infinity, e to the minus st, t to the n plus 1 dt. And the strategy, as usual, will be to knock that power of t down by 1 with the parts formula. So this is the dv part, that is the u part. So the antiderivative is uv, so t to the n plus 1, e to the minus st, and then you divide by a minus s, you get that on the interval from 0 to infinity. And then minus the antiderivative. Well, we know this much is coming, e to the minus st from 0 to infinity. Now, how do you get there? Well, antiderivative here is minus 1 over s, e to the minus st. So that's a plus, and you get an s in the denominator. Then you take the derivative here, du, so that's n plus 1 t to the n. So I've got an n plus 1 in the numerator, t to the n dt, and that's all fine, except that it's so crunched you can't probably read it. So let me recopy it. You get this thing, and by the way, what do you think this is going to contribute to the sum? Probably 0, right? It's what's happened every single time so far. And you're right, it does. At infinity, this turns into a 0. At 0, this factor turns into 0. So that first part goes away, and you're left with this. N plus 1 over s integral 0 to infinity, e to the minus st, t to the n dt. But then when you look at that, you say, oh, wait, I recognize that integral. That is, we'll just copy this part. That is the Laplace transform of t to the n. So the Laplace transform of t to the n plus 1 is n plus 1 over s times the Laplace transform of t to the n. So when you go from t to the n to t to the n plus 1, you pick up a factor of n plus 1 in the numerator, and you pick up a factor of s in the denominator. Okay, so I think we are ready to make some conclusions. What will happen then with t squared? Well, according to this formula, it should be 2 times the transform of t. Whoops, I got that wrong. It's 2 over s times the transform of t. And that is, well, 2 over s times the transform of t is 1 over s squared. So I've got 2 times 1, 2 factorial over s cubed. It does have the cubed in there. But now you can see, well, let's do t cubed. If we use that same pattern, you're going to get a 3 over s multiplying the transform of t squared. But the transform of t squared is known. So I have 3 over s multiplying 2 factorial over s cubed. 3 factorial over s to the 4th. And in general, then, it would appear that t to the n has transformed. Well, let's see what we got. T cubed, 3 factorial. T squared, 2 factorial. T to the 1, that's 1 factorial. And that's t to the 0. And that is indeed 0 factorial over s. So t to the n appears to be n factorial over s to the n plus 1. But we're not quite done, because we know this. gamma n plus 1 is n factorial. So this is also equal to gamma n plus 1 over s to the n plus 1 power. So you actually have that symmetry there. It's just buried in the gamma function. And that gives us at least a reasonable hypothesis for this. What if you had t to the a power, where a now is not an integer? It's positive, but not an integer. So like 3.5 or something like that. Well, a good guess would be that its transform is gamma of a plus 1 over s to the a plus 1. And it would be nice if we could show that that's true, or at least discover what it is instead of this, if that's wrong. So let's give it a try. We will compute one more of these powers of t. So let's get the Laplace transform of t to the a. So now we're thinking of a as being positive, and a is any real number, not necessarily an integer. All right, well, Laplace transform t to the a is integral 0 to infinity e to the minus st t to the a power dt. Now, we could do parts and knock that power down by 1, as long as a were at least 1. But that turns out not to be the best strategy here. It works a little bit better if you do a change of variable. What I'm going to do is let x be equal to st. And then t is equal to x over s. And dt is equal to 1 over s dx. So let's rewrite this integral. Oh, I should probably say this though. When t is 0, if t is 0, well, t is x over s, right? Or you could put it this way. X is s times t. And we've already mentioned this, but I'll write it down again here. S is definitely a positive number. We're not thinking of negatives. If t is 0, then x is positive number s times 0, which is also 0. If t goes off to infinity, then x, well, it's a positive number times t. So that goes off to infinity as well. So what that means is this: the Laplace transform of t to the a is the integral. We're going to change variables in one step here. E to the minus st, t to the a dt. Well, that's equal to, now these are t limits. T equals 0, t equals infinity. These are going to be x limits. But it's still 0 and infinity. We did the change of variable calculations here. Then this is e to the minus x. This t is x over s to the a dx. Let's see. I wish I had not put that equal sign right where I did. When I teach in person, I almost always write this on the board. And I didn't know how much I was going to miss being able to erase. And I tried pencil, but it really does not show up well on the camera. There is. I didn't write it there, did I? Well, what should I do? I can squeeze it in right here. But you're exactly correct. It does belong in there. Okay, now we've got, for the purposes of the integral, the s is fixed. We're thinking of that as constant with respect to t and with respect to x. So we got s to the a in the denominator. We got another s here. So we've got 1 over s to the a plus 1. Then we have e to the minus x. Then we're left with the x here. X to the a dx. But remember, gamma of, well, let's put it this way. Gamma of nu plus 1 is integral e to the minus t, t to the nu dt. So if you wrote this in terms of x, if it'd be gamma of nu plus 1, 0 to an infinity, e to the minus x, x to the a, for instance, you could use here, dt, and that would be a plus 1 in there. So this thing is nothing other than the gamma function. And gamma of a would have an a minus 1 in here. This is gamma of a plus 1. Well, 1 over s to the a plus 1 power is gamma a plus 1 over s to the a plus 1. And that's what we wanted to prove. T to the a power has transformed gamma a plus 1 over s to the a plus 1. And you'll be pleased to know that in the whole list of transform formulas we're going to generate, this one is the hardest. So they get better. And the reason is we start to have some tools. We don't have to do everything from the definition. Okay, well, let's get the transform of an exponential function, e to the at. And the reason is, for doing this, it's the gateway to a whole bunch of other stuff. We're going to get sine, cosine, sinh, cosh, e to the at times sine omega t, and e to the at cosine omega t, all from the breakthrough that comes with this formula. And it turns out this one's especially easy to compute. So next one, what's the Laplace transform of e to the at? This comes up over and over again in this class, e to the at. So I gave it a name. It's the eat function. You don't have to call it that. I suspect you won't find it called that in any serious textbooks, but it helps you remember. Okay, 0 to infinity, e to the minus st, e to the at dt. And well, we got a couple of exponentials. We just add up, we use like base and add the exponents. So integral from 0 to infinity, e to the, well, let's take it in steps, minus st plus at dt. And what I want to do is factor a t off of here. So I'm going to write it this way. I'd like the minus because I want to be able to see explicitly that that's a negative thing. So it's like so. That's how I'm going to start. Oh, dt, of course. Then what I'm left with is s minus s plus a. But if I take the minus out, then I have s minus a. And this can be computed. Now notice, this does not make any sense unless this exponent is negative. So it must be that S is bigger than A. There's a condition on this. S must be greater than A, or it's just not defined. All right, well, if S is bigger than A, though, we just do this in the usual way. It's e to the minus S minus AT. The chain rule factor is negative 1 over S minus A. And you evaluate between 0 and infinity. As t goes to infinity, you have a negative coefficient on t here. So this whole thing collapses. At 0, this becomes e to the 0, which is 1. But of course, it's a minus 1. But then again, you're subtracting because it's the bottom limit, right? So it's minus minus. So you get equals 1 over, and S minus A is just constant. 1 over S minus A. And that, it doesn't look so profound, but turns out to be a huge step forward. So the transform of e to the AT, I didn't line these up very nicely. 1 over S minus A. And this makes sense only when S is more than A. All right, now, because no matter what your final goal is, in this class, for the time being, you're playing the role of mathematician. So of course, when you see e to the AT, instantly what comes to mind is, oh, well, what if we made A equal to minus I omega? That would be a really good idea, because we know that e to the I theta is cosine theta plus I sine theta. So this is the same as the transform of cosine omega t plus I sine omega t. And if you think about it, the transform of a sum of functions is just the sum of the transforms, because what you're going to do is essentially integrate this, multiply by something, right? And the integral is a linear functional. You can, if you have the integral of f plus g, well, that's the integral of f plus the integral of g. So the same thing's going to work with a Laplace transform. So that's the Laplace transform of cosine omega t plus I. The I will just come through the integral sign. Laplace transform of sine omega t. Well, that's a nice start, but it's not quite done. What is the transform of e to the I omega t? Well, no matter what a is, e to the AT has transform 1 over S minus A. So that is 1 over S minus a minus I omega. So all I did is I took this formula right here, 1 over S minus A, and I replaced A by, why did I use a minus? I don't know. It'll work just fine, but you do need to be consistent. How about this, though? This is by far the easier fix. I'm just going to change that to a plus. You can change that to a plus on yours by crossing it the other way. And I computed it here as if it were a plus. And plus is what I want, really. So this is all good here. And now I will have a change right there, though. E to the AT has transformed 1 over S minus A. So this will be 1 over S minus I omega. Okay, now that's great, except things hard to read. So let's multiply this by s plus I omega, top and bottom. And on the left-hand side, then we're going to get s plus I omega in the numerator. In the denominator, we get s squared. Middle terms, of course, cancel out. This is a plus and this is a minus. So this times this is, let's see, it's going to be omega squared for sure. And then you've got a minus I squared. Minus I squared is plus 1. So it's s plus I omega over s squared plus omega squared equals the transform of cosine omega t plus I times the transform of sine omega t. And then you equate real and imaginary parts. So s over s squared plus omega squared is the transform of cosine. And omega, we'll say I omega over s squared plus omega squared equals I transform of sine, then you cancel the i's out. So omega over s squared plus omega squared is the transform of sine omega t. And really, with a calculation that's not terribly difficult, we get 2 more transforms. That's pretty good. And these are very common. You probably will want to remember them. So I'm going to copy them over to my table. I have cosine omega t. It has transform s over s squared plus omega squared, and sine omega t. That has transformed omega over s squared plus omega squared. Something to notice about this, I repeat this to myself over and over again, even now, because it helps me keep these straight. I have no problem recognizing that when I take a sine or a cosine, it's going to be either s or omega over s squared plus omega squared. For some reason, I remember that very easily. Now, remember, s on the right-hand side here, s is the variable. This is an odd function. That is an even function. And this is generally true. If you start with an even function and take its derivative or antiderivative, you get an odd function. And if you start with an odd and you take its derivative or antiderivative, you always get an even. So these integral transforms are carrying that pattern over because they're based on an integral. So you start with an even function, cosine omega t, you've got to transform to an odd, s over s squared plus omega squared. If you replace s by minus s, you get the negative, right? The bottom minus gets killed, but that one survives. Sine omega t, that's an odd function. That omega is a constant. Omega over s squared plus omega squared. It's only got a square on the s, so that's an even function. So odd transforms to even, and even transforms to odd, as it should, since it's based on an integral. Okay, well, how about sinh and cosh? Let's see. Maybe we could just do it this way. We know this. Sinh of AT is 1/2 of e to the AT minus e to the minus AT. So the transform of sinh is, now we're using the linearity of the integral. So we have 1/2 times the transform of e to the at. Well, we know that. That's 1 over s minus a. Subtract the transform of e to the minus at. Well, that's going to be 1 over s plus a. Just exchange a for minus a. And you put those together. Well, let's see. We'll get in the numerator s plus a minus the quantity s minus a over the product s minus a, s plus a, s squared minus a squared. But when you put these pieces together, s minus s is 0. Then you'll have a minus a, that's 2a. But the 2a divided by 2 is a. So that's a over s squared minus a squared. And the Laplace transform of cosh is the same thing. You start from the definition of sinh and cosh. And the only difference is, instead of a minus here, you'll have a plus and a plus here. So that's going to become a 2s. So this, and divide by 2, will be s over s squared minus a squared. And so let's copy that onto the table. Sinh of at has transformed. Now, sinh is an odd function. It should transform to even. So a over s squared minus a squared. And cosh has transformed. Well, that's even, so it transforms to odd. S over s squared minus a squared. And notice how similar those are to the sine and cosine. It's just you exchange this plus down here for a minus. I picked this trick up. It's a memory trick from Kreutzig. I was not so clever as to think of this myself. Notice this is straight out of Kreutzig. He does cosine omega t and sine omega t, but sinh of at and cosh of at. I like that because it helps you keep these formulas straight. These are 4 formulas which are very close, right? So as a memory trick, what Kreutzig always quotes sinh and cosh with an at, and he always quotes sine and cosine with an omega t. And if you stick with that pattern yourself, you will find it helps you keep from crossing them up in memory. You're in the middle of a calculation. You don't want to say the transform of cosine of omega t is s over s squared minus a squared. That'll make the whole calculation fall apart. You don't want to get that as a minus when it should be a plus. So if you switch the letter for the coefficient as well as from sine cosine to sinh cosh, your memory will be less error prone. And why? I don't know. That's just the way humans work. Now, if you're one of those people who has absolutely no trouble remembering formulas, well, good for you. Memorize it any way you like. But I'll stick with Kreutzig's trick because I found that it works for me. Well, I think we are almost there. There is one last one, which is quite, or one last pair. E to the at sine omega t and e to the at cosine omega t. You might recognize that this really is Kreutzig's list. And well, it's everybody's. Everybody does this. What we're doing is just listing the common right-hand sides or functions that might be in the right-hand side when you're doing finding particular solutions by the method of undetermined coefficients. Those are all the kind of functions you can handle with that method. So that's what our list is here. Now, there are long, long tables of Laplace transforms, but for these basic ones, it really is really is very helpful if you know them. Okay, well, let's go after e to the at. Would like to be able to get here sine omega t, and we'd also like to be able to handle cosine omega t. So what if we did this? Laplace transform e to the at, and then we did times e to the I omega. Well, there's more than one way of looking at that. On the one hand, you could say this. E to the I omega is cosine omega t plus I sine omega t. And that would split very nicely into real and imaginary parts. It's the transform of e to the at cosine omega t plus I times transform of e to the at sine omega t. So that's a good way to start. And this one, well, we can just go after this with a little algebra. Okay, if I put those together, I've got e to the, tisk. It's supposed to be a t right there. And notice it appeared over here as if I had it there. So I was thinking it should be there, but I did not write it. E to the a plus I omega t. Well, we know how to transform e to the coefficient times t. It's 1 over s minus that coefficient. Ooh. Well, let's see. That might not be so bad as it looks. 1 over s minus a. We got a real part minus I omega in an imaginary part. So of course, what we'll do is multiply by the conjugate of the denominator. So I got that thing. And I'm going to multiply on the bottom by its conjugate, s minus a plus I omega. And exactly the same thing in the numerator. Whoops. Started to write a plus. And it's not plus. S minus a plus I omega. Okay, multiplying that stuff out, well, we'll get s minus a squared plus omega squared over, and then I'll get, for the real part in the numerator, s minus a, and for the imaginary part, plus I omega. And that is that. So let me copy this down here, except I'm going to split it into real and imaginary parts. It's the Laplace transform of e to the at cosine omega t plus I times the Laplace transform of e to the at sine omega t. And it was a bit of a squeeze, but it worked. So the transform of e to the at cosine omega t, well, you equate the real parts. So this is a real plus an imaginary over a real. So you get the real part, s minus a over s minus a squared plus omega squared. And the transform of the corresponding function with a sign in it, e to the at sine omega t, it's the imaginary part of this function up here. So omega over s minus a squared plus omega squared. And so in only a little over an hour, we generate our basic building blocks. Oh, I wanted that goes with cosine, not sine. This should be just omega up here. Okay, so there's the completion of our basic table. And I did announce a plan way back at the beginning. What we need to know is how to transform some common function of, calculus, science, and engineering. And we just got that done. Now we need to know how to transform derivatives. Turns out that's much easier. And a good thing, because we don't have that much time. All right, so let's figure out how to take the transform of the derivative of f. Well, since we have nothing else to work with, we write down the definition. And we say that is just kind of begging to be treated this way. Here is dv, and here is u. So let's use the parts formula. U e to the minus st times v, well, that'd be the antiderivative of the derivative of f at t. Minus v, that's f at t, du, well, take the derivative of e to the minus st, you get e to the minus st back again, and then a chain rule factor of minus s. Okay, now, we have seen this so many times, and it's just a little bit different this time. What happens when you let t run off to infinity? Well, this thing gets crushed down to 0, so it'll delete that. As long as this doesn't grow faster than an exponential, you'll get a 0 when you plug in infinity. Then, notice there's no negative sign here this time. Then, when I plug in the 0, I get e to the 0, which is 1, and f at 0. So I actually get minus f at 0 coming out of this piece right here. This piece, on the other hand, well, that's s times a very familiar integral, s times the transform of f at t. And that is of course, we don't usually bother with writing the zero. So the standard way of writing this is this: the Laplace transform of f prime at t is equal to s. Now, it's the transform of little f at t, but the standard way of writing that is capital F at s. It's s f at s minus little f at 0. And we now can solve, we've got enough to solve first order equations, at least some. How about the second derivative? Well, that would be the derivative of the first derivative, right? So what you'd want to do is apply this rule to the second derivative. So taking off one derivative, that notice I went from f prime down to f here. So I'm going to go from f double prime down to f prime. And now I plug in what I had on the previous step here, s f at s minus little f at 0, close the bracket, minus f prime at 0. And so I've got Laplace transform of second derivative of f, little f, is s squared, capital F at s, minus s, little f at 0, minus little f prime at 0. And these things right here, f at 0, f prime at 0, these are your initial conditions, or initial values. When you solve, you have an initial value problem, you have an ODE, and then you have, furthermore, you know the value of the function, and the value is first derivative at typically 0. So it's just set up perfectly for that. So taking a derivative essentially is taking a derivative in the t space multiplies by s in the s space. So you're changing differentiation into multiplication. And it also turns out, I think for, in the interest of time, I'll just quote the result. It's even simpler for integrals. If you take the integral from 0 to t of f of x dx, the transform of that integral, that's a function of t, of course, is simply 1 over s f at s. So differentiating multiplies by s or s squared, plus some detail, and integrating with integrating in the t space will turn into dividing by s in the s space. And that's how calculus problems get turned into algebra problems. You're changing derivatives and integrals into multiplication by s or dividing by s. So, and you know, there's some details occasionally for the derivatives. But that is really what we need to get started to solve some differential equations. And now there is one other thing on the list here, which is, well, you got to know how to back out of this transformation process, right? You started with a little f at t, and now you've got stuff in terms of capital F at s. Well, how do you get back? Well, I probably can just show you in context. So I'll try this to jump to some differential equations and be able to get a couple of things done at once. So let's take something simple. Okay, how about this? Y y double prime plus y equals 0. And, oh, how about this? Y at 0 equals 1. Y prime at 0 equals minus 1. I'm making up numbers. Now, we know what the solution is here, right? You have sine, essentially sine and cosine will solve this. And then these initial conditions will serve to fix the coefficients. So it's going to be some number times sine of t plus some number times cosine of t. So we don't really need Laplace transforms to do this, but we're going to do it anyway. So you take the Laplace transform on both sides. Now this, of course, is pretty simple. When you take the integral of e to the minus st times 0, doesn't matter what the limits are, you're going to get 0. So the right-hand side is still going to be 0, but y double prime, I need to deal with that. So I have a formula. When I take the transform of the second derivative of the function, I get s squared times the transform of the function. S squared f at s minus s, take its first, its initial value, y at 0, it's right here, and then minus y prime at 0. So the s goes with the y at 0, and the y prime at 0 stands alone, and that is transforming y double prime. So maybe I should try to make some note here. And if you don't like all this stuff cluttering up your notes, well, just leave that out. Okay, now I got to transform y. Well, there you go, transform y. And I got to transform 0, that's 0. So there it is. Oh, and I'm mixing my metaphors here. The transform of little y, traditionally you use capital Y, and I used a capital F. So when my whiteout dries, I'll change that to capital Y. But in the meantime, capital Y, it's invisible right now, but it's there. S squared capital Y plus Y. So I've got S squared plus 1 times capital Y at S. And then I have these other terms, which I'll just push over to the other side of the equation. So plus S Y at 0 plus Y prime at 0. But of course, I know what those are. Y at 0 is 1, and Y prime at 0 is minus 1. Those are the initial conditions. So this is plus S times 1 minus 1. So S squared plus 1, cap Y of S equals S minus 1. So Y at S equals S minus 1 over S squared plus 1. And we're almost done. This one is easy to transform back.
Where did the S squared plus 1 come from?
Right here. Oh, okay. I never got back to this. So I've got S squared multiplying cap Y, and if you will, 1 multiplying cap Y. So S squared plus 1 times cap Y.
Oh,
And I put those other terms on the other side. Okay, now I'm just going to split this up And the reason I'm going to split it up, if you don't see it already, you'll instantly see in a moment. I'm going to go shopping in my list of transforms to see if I have anything that looks like s over s squared plus 1 and anything that looks like 1 over s squared plus 1. Well, you zip through here and you say, oh yeah, those look a lot like the transforms of cosine and sine, right? If you got s over s squared plus omega squared, in this case 1 squared, then that is the transform of cosine. And if you have omega, well, if you have 1 over s squared plus 1 squared, that's the transform of sine. So y at s equals s over, I'm just trying to clean this up, minus 1 over s squared plus 1. So little y at t is the function that would have this transform. Now, what we usually do, though, is write this. So what I'm mostly writing here is just the notation. We say the inverse transform. Find the function whose transform is. I shouldn't say plus, it's minus, right? Minus inverse transform 1 over s squared plus 1. And, well, the function that transforms s over s squared plus 1 is cosine of t. And the function that transforms to this is sine of t. So that's done. It's got the initial conditions already in here. They came in right at this point where we evaluated y at 0 and y prime at 0. So there it is. Let's just check this. Certainly sine and cosine would satisfy this ODE. If you take two derivatives on cosine, you get minus cosine. You take two derivatives on sine, you get minus sine. But did we get the initial conditions? Well, at 0, this function is equal to 1, which it's supposed to be, and its derivative, y prime, derivative of cosine is minus sine, and derivative of sine is cosine. So if I put in a 0 on this, I get 0 here and minus 1 here. And that's what it was supposed to turn out to be. So it worked. And this is the standard feature of Laplace transforms. Usually we're solving for an initial value problem. And you know, you might even have a non-zero right-hand side. It just is all done in one swoop. The swoop may be long and painful, but it's all done with one of them. So, and notice how this is exactly what we did. We started with an ODE, we took a transform, and when we took the transform, it turned two derivatives into multiplication by s squared and some detail. And well, here you're just transforming. And then we did algebra to get to solve for y of s. And here, and then we kind of split things up nicely so we could observe these in the table. And then we took the inverse transform, which is what this says. Start with the ODE, transform, do some algebra, inverse transform, you're done. And that's what we did here. Now, a reasonable person might think this though. Well, hold on. Not every ODE comes to me as an initial value problem. What if I don't have the initial conditions? I'm kind of in trouble then, right? Well, not really. Why don't we do another one of these? And I think, how about this? Y double prime plus, no, let's not make plus. Let's make this one a minus, just so we have some variety here. I'm trying to keep these simple enough that we can do them in not too much time. How about minus 9y equals 0? And what are the initial conditions? Don't have it. So if we were going to do this by Laplace transforms, move this down on the camera. If we're going to do this by Laplace transforms, then the transform of this is s squared cap y at s minus s y at 0 minus y prime at 0. But of course, I don't know those numbers. And then the transform of minus 9y is just minus 9 cap y at s. And the transform of 0 is 0. So what you do in a case like this is you say, well, I don't know, think of something. I'll say y at 0 is C1 and y prime at 0 is C2. I don't know what those numbers are, but they're constant. So that's certainly legal. So now I have this situation. The cap y is multiplied by s squared and minus 9. So I have s squared minus 9 cap y of s. And then I'll push these over to the other side equals C1 times s plus C2. No, it's the other way around. C2 times s plus C1. Anyway, two constants. And I solve for cap y algebraically. That's what this means right here. To go from here to here by algebra, we're solving for cap y. So solving for cap y, I get C2s plus C1 over s squared minus 3 squared. And then how we solve this, the final step is, as usual, we go shopping in the list of transforms. Do we have anything that looks like a difference of squares in the denominator? Well, we sure do, sinh and cosh, right? So s squared minus a squared on the bottom, for both of those, if you have s in the numerator, that came from cosh at. If you have a in the numerator, that came from sinh at. So we're going to want to do something very much like what we did for sine and cosine. We'll just split these, only I'll write it this way. S over s squared minus 3 squared. And I'll just write this C2 off to the side here, C2 times that. Plus, well, probably I'll want this. I would like this to say 3 over s squared minus 3 squared, because in this form, if you have s squared minus a squared, you want an a on the top. Now, I can get that easily enough. It already had a C1, so I just have C1 divided by 3. So those 3's cancel. And now, taking inverse transforms, what function of t has transformed s over s squared minus 3 squared? Well, the answer is C2 goes on to the right, of course. This is an odd function. It came from the even cosh at, 3t. We know what a is. Well, I'll do it that way for now. I'll fix it next step. Plus C1 over 3. And this one came from the sinh of 3t. So one more step to clean this up. C2 cosh at. And now, an arbitrary constant divided by 3, after all, is an arbitrary constant, right? So I could just give that a new name. C3 sinh 3t. So I can solve problems that don't have initial conditions. I I just give the unknown numbers a name. C1, C2, whatever you like. You know, if you were clever about this, you know, you'd wait to fill that out. And later on, you'd say, oh, this is not C2, this is 3 times, oh, not C1, it's 3 times C1, because then the 3's would cancel out. But it doesn't matter. This way works just as well. A constant times cosh plus a constant times sinh of 3t. And I said I was going to put a 3 in there on the next pass, and I didn't yet. The only thing to survive from the age of typewriters, by the way, is whiteout. We had these old typewriters way back. They were strictly mechanical. It was nothing electronic. And push the buttons hard, and they would stamp ink on your page. And people noticed that they tended to push the wrong button every now and then. So someone invented whiteout, and it has survived. As long as there's paper, we'll have it. Okay, so there's a couple of ODEs we've solved by using Laplace transforms. Let me maybe do one more thing. What if we wanted there are some homework problems that look something like this. Suppose you had a function like so. On the interval from 0 to a, this thing jumps up to, let's say it's, in this case, it's 1. But then it drops back to 0 and goes like that. So it's an on-ramp function. It starts at 0, ramps up to 1, and then it drops back on the interval from 0 to a. Or if you wanted a simpler version, you take it from the 0 to 1. Let's say that this thing is f of t. So how do you transform this? Well, it's straightforward, actually. What you do is you write a formula for this, but you write a piecewise formula. F at t is equal to, well, it's just the equation of a straight line on the interval from 0 to a. So let's see, the slope, the rise is 1 and the run is a, so it's t over a on the interval from 0 less than or equal to t less than, now you can make it equal to or not, it's not going to matter for the integral, up to a. And once t gets beyond a, it's 0. So then you split this function over 2 intervals. On the interval from 0 to a, it's e to the minus st times t over a. And on the interval from a to infinity, it's the 0 function. So this part obviously makes no contribution to the transform. And now we just have to do this. And of course, this is a classic application of integration by parts. I'm going to just factor the 1 over a out. So I'm going to take I want the antiderivative of e to the minus st times t. And the t part, that is the u, and this part, that is the dv. Okay, so we're going to have u v e to the minus st over s Now, not on 0 to infinity, 0 to a, minus integral from 0 to a. V is once again e to the minus st times minus 1 over s. And du is dt. And that's messy, but I think we can figure it out. Okay. When you plug in the a, 1 over a on everything. When you plug in the a here for t, you get a e to the minus as. So just plugging in a for t, all over s. And when you plug in the 0, you kill it off because the t is multiplying the rest of it. So minus 0. And this, well, the antiderivative of e to the minus st is minus e to the minus st over s. So minus e to the minus st, but we had another s there. So over s squared on the interval from 0 to a. Oh, but making a mistake here. Square bracket here, everything gets multiplied by 1 over a, right? Okay, well, this one is easy. That a and that a cancel out. So I've got e to the minus as over s. And this one, I just have to figure out what this looks like and then don't lose track of the 1 over a. All right, at a, I've got e to the minus as over s squared, but it's negative. And I need to multiply it on the bottom by a. And when I plug in the 0, I get plus 1 over s squared. And then you pick up an a there. Ah. Well, for making up a problem, it came out nice. Well, no, it's not quite as nice as I thought those would add out. They don't, because this doesn't have an a in the denominator. But it will. You can make it look nicer. Multiply the first one up and down by a e to the minus as. This one minus e to the minus as plus 1 all over, oh, I need an s here as well, as squared. So you can transform such things. And that is hinting at where we're going. How would you solve, by the techniques we've had earlier in the class, how would you solve a differential equation that had its right-hand side, say, equal to this f of t? Well, we can write a formula for it, but we have no idea what to do with the thing. You know, for all of our techniques so far, they just simply don't apply to that sort of a function. So you can use Laplace transforms to solve such functions, and that really is really where we're going next. The next lecture, we'll talk about transforming ut minus a, which is the function that looks like 0 if t is less than a, and 1 if t is more than a. What it's equal to at a doesn't matter because we're talking about integrals. And then also the delta Dirac function, which you think of it this way. It's equal to 0 if t is not equal to a. It's equal to, well, infinity if t is equal to a. And it has this property. If you integrate on any interval containing a, and sort of the custom in mathematics to say a little positive number, epsilon, and they may be different. So if you just go a little bit to the left of a and a little bit to the right of a, no matter how small, if you integrate this thing, you get 1. Now, there's no classical mathematical function that has that property. You know, it's 0 everywhere except 1 point. And then when you integrate over that point, you get 1. No, there is no function like that. However, nature acts that way. At least if you believe atomic theory of matter, think about having, say, an electron at some point in space. Well, if you're trying to compute the charge over a region, what you do is you integrate over that region. So if you integrate over that one tiny little point that's got the electron, bang, you get a charge of -1. And if you have 5 or 6 of them, you know, in there, and you integrate over the place where those 5 or 6 electrons are, you pick up a charge of -5 or 6. So nature, at least we think, seems to behave like this in certain kind of cases. This is just a one dimension, but you know, you could generalize this to 3. So shouldn't we have mathematics that works for that? And the answer is yes, we should, and yes, we do. And these are the theory of such things, which this sort of thing, these are called in general functions, and you've been doing calculus functions for a long time. These things are at least sometimes called distributions, and that's borrowing a term from probability theory. So they're a generalized form of functions, and it's great. You can actually solve problems, and you can model them. You know, you can get graphs and all and everything else. So that's coming up next, and that really is the reason that we're doing Laplace transforms. Well, 2 reasons. Number one, you're almost certain to encounter them, and so if I don't tell you, then in your, say, electrical engineering course, sooner or later you get to Laplace transforms and you say, I've never heard of these before. And your professor will say, where did you take differential equations? And it'll get traced back to me. So I have to tell you. But then number 2, it just greatly expands the scope of the problems that we can do. And they're practical, realistic problems. Okay, well, that's it for tonight. So I'm going to be posting the printed notes for this, which will have problems in it. You do have an assignment that's due on Thursday. Don't forget that.
I have a question about it.
Okay.
In the problem where it's asking to graph the solution, it says to let ODE modify to the step size, and then interpolate its points with the cubic spline function. Should we graph the function with the broken line, or just straight to the curve?
Normally, for the benefit of people listening online, in the homework assignment, it says to solve an ODE with the ODE 4-5 function, and then interpolate those points with a cubic spline. And the question was, okay, so what exactly do we graph? And the answer is the standard way to graph that would be to graph the dots in addition to the smooth curve that comes from the spline. Yes, unless it says otherwise. And there are some cases like the phase plane. I think I said leave the dots out. And it's not really so important whether you leave the dots out. I just want you to get familiar enough with MATLAB that you're capable of putting the dots in or leaving the dots out at will. Okay, so that's the only reason I said to leave them out there. Linda, do you have a question?
So this about graphing it, draw the graph out on paper after putting it through MATLAB, we have to include the dots as well.
No, with MATLAB, you can force it to draw the dots or not to draw the dots. So for instance, let's suppose I've run ODE 4.5. And by the way, let me just say this, class is over. So if you're done listening, you're welcome to sign offline or leave the classroom, whatever is convenient. But okay, so let's suppose I've run ODE 4.5. And so now I've got my T's in here, and I've got Y and Y prime as two different columns in here. If I think when I did it, I did something like this. YY is spline. Oh, well, you set up your XX. And essentially that goes from A to B minus A over N. Is the step size to B. I'm sort of mixing MATLAB code with mathematical notation. But so like if you want 500 or 501 dots, you set that N to be 500. Okay, so this sets up your interval. Then what you're really, no matter what you're doing, you're always plotting dots, right? So you're turning a pixel on or you're leaving it off. But what you do is you try to pack them in close enough so that they look smooth to the human eye. So then you have to tell it where you want those, the points you want to interpolate. And then you can do this all in one. You could do this with ppval on in the next step, but you can create the spline and compute the points all at once. So you tell it, evaluate this at XX. Okay, and if you're going to do that many, you probably want to sum up. All right, so now you've got your smooth curve in the pairs XX and YY. You've got your dots in T and Y colon comma 1. So if you do a plot, if you do T comma Y colon comma 1, this much plots dots. And then you can give it more instructions all in the same command. You don't have to do the hold on and hold off stuff. You just do it all at once. And then you can say, okay, now plot XX and YY. This part will plot the spline curve. Now, if you don't want the dots, you just leave it out. If you do want the dots, you put it in. Does that make sense?
Yeah. I wasn't when you do a homework. This is I've been sort of probably graphs from that on paper.
Oh, here's what I would recommend. You run the code now. It doesn't matter whether you're doing it online at say Octave Online or you're doing it on your own computer or whatever. Then if it's on Windows, for instance, there's an app called Snipping Tool. You just take a piece of a screenshot, and then you can paste that into a say a Microsoft Word document or something. So that's what I'd like to see, because what I'm trying to find out is whether you can run the MATLAB code to make it work. Now, if you're actually running MATLAB or you're actually running Octave, I think you have other options, but it's still good enough to take a partial screenshot. That's still acceptable. I don't care if you learn about all their graphics functions right now. It's good enough to know how to solve DEs and get good sketches. If you have trouble with that, just ask me another question. Oh yeah. Okay.
I did notice you can export a PNG image or something, but it doesn't keep the dots in.
Oh, it leaves the dots out.
At least when I was doing Octave online, it didn't keep the dots, or I don't think it kept the scale on the axes either.
Oh,
I
okay.
think it was just a line.
Oh, that's too bad.
The snipping tool worked.
Yeah, what I do is really pretty crude. I just do snipping tool, and I'm sure there's something similar on Mac
Yeah.
and Linux.
Well, good night. We'll see you Thursday.
Yep.
I don't really understand about the code stuff.
Oh, okay, sure. Let me just check to make sure I don't have questions in the chat here. No, I don't.